I'm going to tell you about the graph mining project that we have had at Google for the past 7 years. So before I start and diving into the details, let me tell you where I'm coming from. We have an algorithm research group in New York at Google New York office, where we have basically groups working on market algorithms, large-scale graph mining, and large-scale optimization. And the graph mining project is the project that actually empowers these other projects that we are working on with many other teams. Like, if you want to know more about our involvement, and like basically the talk I'm going to give is mostly about the papers that we have written. They're all available in our webpage. In the area of graph mining, we have basically we have been working on different aspects of machine learning empowered graph mining techniques and algorithmic foundations, and also like research on hybrid algorithm and system systems that like have algorithms aligned with the right underlying system. So yeah, now I'll try to tell you a story of the graph mining project. For this audience, I don't need to convince you that graphs are everywhere. You can model many different semi-supervised learning, unsupervised learning problems, data mining problem, information retrieval problems as graphs. And we actually work with tens of different types of graphs at Google, like advertisers that get clicks on the similar keywords, social graphs, local business map graphs, co-watch videos on YouTube, and so on and so forth. So the mission of the graph mining project is to develop the most scalable graph mining library at Google, and we aim for graphs that are like that have like trillions of edges, and we try to apply different type of systems like MapReduce, distributed hash table service, and like other systems to develop this library. So other than developing the library of different type of tools that I'll tell you about, we apply these to different types of products at Google, and we work with the engineering teams to deploy these. So we have to make sure that we develop a system that is like easy to use and also does not need too much babysitting. So like fault tolerance, for example, becomes very important in the development of the algorithms and the library. So like if we have like an algorithm that runs on many machines 80% of the time, is completely useless, because if you want to have like this in a production system that runs every so often, you want to make sure that you don't need to babysit this system. And like that actually changed like several times our algorithmic approaches and so on and so forth. And then we also work on algorithmic foundations and of these problems. That will be the focus of this talk. Along the way, we also compare different type of frameworks. So this is an overview of the tools that we provide, for example, in this library, to give you a sense. So like I'm trying to give you basically a short story of how we developed this and like what are the challenges that we have encountered, like the journey. Like we ended up basically building these 6 families of tools. The first one that we call a graph building is where we take your data set and we build a nearest neighbor graph out of it. So at the beginning of the project, we did not have this, and we were like missing an important piece for our clients. So like there are social graphs around and so on, but if you don't have them, if you have to build them, that's like actually the first important challenge. So that's like where we use locally sensitive hashing, like local neighborhood graph search to build the nearest neighbor graphs. And then we have a set of like clustering tools, what we call balanced partitioning tools that try to divide the graph into like equal pieces, pairwise similarity or link prediction tools, and then label prediction tools on top of nodes, and then tools that compute centrality score. So this is like basically the set of tools that we have learned over time that are very useful in like a company like Google, like in data mining environments. Before diving into like specific stories, let me also emphasize that we work with like many clients and many applications at Google. So these are the 4, for example, application areas that we have identified. There are like spam and fraud detection tools in which we basically use like several of graph mining tools. In image search and image quality, like these like tools become very useful. In the context of AdWords, like bidding and keyword matching in AdWords, these things are like query clustering becomes very useful and important. And then we can basically use these tools to identify duplicates in different type of environments, like local businesses and web search. Just to dive into one of the applications for fraud and spam detection, this is also very familiar to this audience, but the way that we apply like some of our tools are either through some variant of label prediction or label propagation. So you have some fraud or spam score on top of a set of nodes, and you want to basically predict the same type of score on other nodes. So these nodes can be entities, and we can relate them based on their relation of different type. We can also use graph mining tools to detect like anomalous, like anomaly, like basically inside the graph, where, like for example, we identify dense subgraphs as like suspicious. Basically activity among some clients, among some entities. So now, in order to tell you the story, I want to go through like 3 sections, and in each section give you 2 stories. The first section is, why do we need scalable graph mining? Why can't we achieve everything with machine learning tools or neural networks or something? So these are like basically 2 specific places that we found that like graphs are very useful. So I want to start with these 2 short stories. The first story is about EgoNet clustering and in EgoNet mining. And this is a joint work with my colleagues at Google. Alessandro is around at KDD, and he has a paper about this, so you can find it later. So the context of this paper was about finding multi-hop similarity scores in graphs or doing link prediction. This is like a very familiar topic to this audience. This can be used in different type of collaborative filtering and recommender systems. So like we all know of different type of similarity score that one can define on top of these graphs. You can take the number of common neighbors, Jaccard coefficient, Adamic Adar, blah, blah. So the idea here was basically to see where these type of multi-hop scores go wrong. And this example shows like the idea behind the using EgoNets to improve friend suggestion. So like in situations that we have a central person who has like 2 types of network connected to it, we can look at the EgoNet of that person and like remove that person from this subgraph and then cluster the underlying like graph. So like in this toy example, this person, the blue person, has basically 2 completely different subsets of like friends. So if we cluster that EgoNet, we get to these 2 subsets. So the idea is, instead of like, for example, counting the number of common neighbors, do this type of EgoNet clustering for each node in the network in a scalable manner, and then try to count the number of clusters that 2 nodes share. So in this case, for example, the red guy and the green guy should not get some similarity through this central person because they belong to different clusters. So like I would not increase the score between the red guy and the green guy. And like that will give me different ways to apply like EGONet score. I can simply count the number of clusters that these two, like each two nodes in the graph belong to among all the EGONets, or I can look at other measures among these networks. So this one we had basically deployed in like a system, like a friend suggestion system that already had several existing features, and we showed that like offline evaluation, it improved the quality of the prediction like by a good margin, and also in live experiments it showed like good promise. So this is what we reported in the VLDB paper, and you can take a look more over there. The second topic, the story of like application that came from application, is this idea of a public-private graph computation model, where we are given a graph, like a social network or something, and then each node in this graph also has a private set of like edges that is only private to that node. So we can't use those edges in recommender system or like in recommending friends for other users. We can only use it for that node V. So that we denote by G of V. The problem is to solve like a general graph problem, like a recommender system problem on each node of V in the graph, on graph G, which is the public graph, plus G of V. So we are trying to solve n different problems. N is the number of nodes in the graph. And just resolving this problem for each node in the graph is computationally heavy. Like we can't do that. We can't start from scratch for each node. So the idea would be to solve the problem first on the public graph, and then after getting the solution, let's say amend this solution with some techniques using the private graph related to basically each node. And the goal is to do this in a way that the running time of amending this solution on the public graph to each of the nodes is proportional to the size of the private part of the graph, private set of edges for node V. So like not to spend too much time proportional to the whole data set. And if we don't do that, it's going to be computationally infeasible to do this for all nodes. So, and like in the paper, we look at different type of graph computation problems, like link prediction problem, number of common neighbors, personalized page rank. We also look at different type of clustering problems, like connected component, shortest path problems, and centrality score computation problems, and basically present like a set of sketching techniques that would achieve basically better algorithms in this context. I'm not elaborating on this because I'm going to focus on other parts of the library and in this talk, but we also confirm the effectiveness of these algorithms like on some data sets, and this is a paper that appeared in KDD last year. And as I said, Alessandro is going to, yeah, not on this topic. So yes, so that was basically the first part where I gave you two stories. Now I want to give you a couple of ideas of algorithmic techniques that we use to develop the tools in the library. In particular, so these are the 4 types of techniques I can highlight. We like solve balanced partitioning problems using some embedding techniques. I'll elaborate on that. We use sample and prune techniques to deal with like very large graphs. Sometimes you don't deal with the whole graph. You sample and solve the problem on the sample. We also use this distributed optimization technique that I'll elaborate on like in the next couple of slides. And then also we use local random walks to optimize conductance and cuts. So I'm going to tell you about, like elaborate on the balanced partitioning piece of the library and the distributed optimization tools that we developed based on composable coresets. The first part is more empirical. The second part is very theoretical, and I'll give you the algorithmic ideas. So For the distributed balance partitioning problem, this is the joint work with two of my colleagues. So the problem we are trying to solve is we are given a large graph with edge weights and node weights, let's say. And we want to divide the graph into almost equal pieces and minimize the interaction between different parts of the graph. So this has applications in basically different areas, and I'll have a slide about that. So sometimes we want to minimize communication complexity in distributed computation. Sometimes we want to minimize the multi-shard queries in a serving system. So the three application areas that we found at Google are basically related to serving the Google Maps directions, like the back end of serving. So like over there, when you declare a source destination like query, these queries are served across like different servers. And here, like, we want to minimize the multi-server source destination pairs. For any source destination pairs that end up in two different servers, we burn much more CPU. So we want to minimize that. So we had a successful story that we actually report in the paper. And the other two application areas we don't report in the paper, and we are like working on like writing a paper on those. But we can like tell you like at a high level that we are using it also in the back end of search, where we try to put queries with similar affinity in the same like server, and that gives us much better caching properties, and we improve the basically memory or flash bandwidth of back end of search by a big margin. But that's been very successful in this application area. And we also facilitate different type of A/B experiments in advertising environment. And this is an ongoing set of work that you have seen, maybe like similar efforts, and like we are getting actually, we are deploying it into some systems like advertiser experiment systems at Google. So what is the algorithm that we deploy here for balance partitioning? So balance partitioning problem is an NP-hard problem even for small graphs. So if I give you a graph with 100 nodes, you want to solve this problem, like it's even not approximable within a factor better than a square root of log n. And if you want to, like, that approximation algorithm is also based on solving some semi-definite program. So it's a very hard problem. Unlike some other problems that I mentioned, clustering problems and so on, that are at least polynomial time solvable, the problem we are trying to solve is NP-hard even on small graphs. Now we want to develop a distributed tool that solves it for any size graph. So this is the type of algorithm that we deployed. It's a heuristic. And like the main interesting idea is in the first step of the algorithm that we found very effective, and we tried many, like tens of different techniques and converged to this method. So first of all, as a first step, we compute basically an embedding of nodes of the graph into a line. And this is what we call an initial ordering. We use either some space filling curves or like for geographs, or like some hierarchical clustering techniques that I'll tell you for general graphs in this stage. So now we have an ordering of nodes, and like we use this ordering in further steps to improve the semi-local moves that we have. So we do like some local improvements on the cut, and like we use this ordering to divide the graph, for example, into pieces, and like in the MapReduce framework, let each mapper deal with part of the graph. So this gives us also like these chunks that we want to like apply the local improvements. So basically, when we have this ordering, we can apply different type of local improvements like random swaps. And then at the end of the day, we can also go after introducing some imbalance and improving the cut value. So that's like the general description of the problem. So as I said, the most effective, important part of the algorithm is actually the first step of the algorithm, where we basically embed the nodes of the graph into a line. And for that, if we have a geograph, we have some coordinates for each node. So we use the coordinates to basically with a space filling curve. Or like for general graphs, we don't have such coordinates. So what we do is we take the nodes of the graph, we compute basically similarity between nodes based on like how connected they are in the network. And then we basically cluster these nodes in a hierarchical way. So the hierarchical clustering will give us an order of nodes, because we can look at basically the order of leaves of the, in this hierarchical clustering, the nodes of the graph will be the leaves of the tree, and we can use the order of the leaves to determine for the linear embedding. And this, and for similarity metric on top of edges, we use a sketching technique to count the number of common neighbors, for example. And this is very effective in finding a good linear embedding, and I'll tell you with some empirical evidence of that. So on the paper, we report the quality of these algorithms on a set of publicly available graphs. So the publicly available ones are not that large. They are in the order of billion edges, but these are the ones that we had some like benchmark to compare with. We couldn't report or compare with externally available algorithms on the other larger graphs. So to summarize parts of the empirical study of these algorithms, we compared, for example, with the best, with this paper called Spinner. That's like a Pregel-based implementation. And then also with the label propagation technique that was reported in a paper like in 2013 based on label propagation. So like what we observed was that on this live journal graph, for example, if I want to divide the graph into 20 pieces, the let's say the label propagation technique basically results in a cut that cuts like 37% of the edges. Even in the linear embedding stage of our algorithm, we beat that. We get to 35%. And when we apply these improvements, these local improvements on top of that, we get to 27%. So we get a better cut, like by 20-something% improvement. Not only that, we also get a like exact balance partitioning. In their case, they had like a balance partitioning with 5% error, like on the size of clusters. So basically, for like this graph and against like partitioning to like 20, 40, 60, and so on, we beat like all the benchmarks, and also both in terms of the value of the cut and also in terms of the balancedness of the cut. We also compare with some other papers like the Fennel and the Metis, which is basically not distributed, like in-memory single machine implementation. So we managed to run this algorithm on basically some graphs. This is for the Twitter graph. Like in this case, we beat the benchmarks for partitioning to 4 and 8, but not for k equal to 2. So our algorithm is very suitable for cases that you want to divide the graph into many almost balanced pieces. Because we do this basically button-up type clustering from the beginning, it's very suitable for like partitioning the graph into many, many pieces. So this is the type of tool that is very effective in other applications, where we also want to put minimum and maximum size on the clusters that we generate. And this is also used in some other applications. The other line of work I want to tell you in terms of algorithmic techniques is this line of work where we use composable coresets in improving the basically quality of different optimization problems. So this is the most theoretical part of the talk. And after this, I'll switch to like more algorithm and system combination. So first of all, with this composable coreset technique, we solve different variants of diversity maximization, clustering, and submodular maximization problems. So the applications of the diversity and submodular maximization problem are in recommender systems, where we want to come up with like diverse search results or diverse news articles in a recommender system. They are also used for data summarization or exemplar sampling. And they can be used also in the context of feature selection in general. And like we have some like applications in one of the papers that we reported on arXiv. And like this has been explored also in the machine learning literature. So that was like two slides about the motivation of these problems. Let me tell you about the composable coreset idea. So let's say you have a data set of size n, and it doesn't fit on one machine. So you have to somehow distribute your computation. The simplest idea to apply is to say, okay, like divide your data somehow into m machines, then run some algorithm on each machine, take the output of each algorithm. So from set ti, you produce a subset of like, or a sketch of the elements si, and then you look at the selected items, and if the size of the data is not too much and you have enough machines, maybe you can basically now take the union of these sets si and run another algorithm on top of that. So I want to see what are these algorithms alg and alg prime that I can apply in the first and the second stage of this process in a way that the output that I produce is a good solution to the original problem that I want to solve. So I say that this algorithm alg is a good composable coreset if it can produce a solution si that basically when I take the union of these solutions, I still have a good optimum solution inside the selected items. So that's the like very general idea. So we applied this idea to 5-6 different problems so far in the past 2 years. So in all of these problems, I'm given basically like a ground set of items, and I want to choose a subset of items, let's say of cardinality at most k, and maximize the set function f of s. So for any subset of items, we can define a function f of s, and we want to find the subset with cardinality k that maximizes the set function. So I can define diversity maximization problems, capacitated clustering problems, coverage submodular maximization problems, and column subset selection problems in this framework. So I'm going to tell you about diversity, clustering, and submodular maximization problems, and not column subset selection. So the diversity maximization problem is where I'm given endpoints in a metric space, and I want to find a set S of k points with maximum diversity. The diversity is the sum of the pairwise distances of elements that I choose. So I can define diversity like this, or like there are two, 3 other variants of diversity function that I can define on the metric space. So it's an NP-hard problem, but you can easily get a 2 approximation for this problem by running a local search algorithm or some variant of the greedy algorithm. So let's see what happens if I want to solve this problem in a distributed manner. So I know that local search is a good algorithm for this problem. What we showed was that, for example, if you apply that local search, if you take the data set, the points, divide them arbitrarily to m machines, apply the local search algorithm, get k points from each side, and then take the union of those, apply again the local search algorithm on it, at the end of the day, you get a constant factor approximation. And basically, in this setting, even random partitioning can give you some good performance, and like arbitrary partitioning give you constant factor approximation. But then if you go to random partitioning, you get better approximation factors. So these are the two, like for example, two theorems that we can show in this context. If you apply local search in both steps, you get a constant factor approximation, but the constant is large. And if you want to achieve the best possible approximation for this problem, which is the 2 approximation, it's possible to tweak the algorithm in the first and second round and get a 2 approximation for this problem. So this is an easy problem to solve in a distributed manner. The other class of problems that are more popular are clustering problems, where, for example, you want to set, like given a metric space, you want to find k-centers. In the k-center problem, you want to minimize the maximum distance of any point to the center. In the k-means problem, you want to minimize the sum of distances to the sum of square distances to the centers. And for the k-median problem, you want to minimize the average distance of nodes to centers. So there is a mismatch between the formulas and the name of the problem. So the goal is to develop a basically general distributed algorithm for this problem. And the framework that we apply is, again, a composable coreset framework, where we divide the data into k chunks, like m chunks, vm to v1 to vm arbitrarily even. So let's say the colors are, each color represent like one chunk. And then like we solve the problem on each chunk, and then take the union and solve the problem on the union. So, wait. Yeah, so like what we can show actually for this problem is, even if we have capacity constraint on top of the cluster sizes, we can amend basically the composable coreset idea to what we call mapping coresets. So we come up with centers for each machine, and then we also find an allocation of the nodes on each machine to the center on that machine, and then basically reconstruct the solution by looking at that matching. So, like again, like we can prove in a general framework that this idea applies here. And like on data sets, for example, we look at like a US map graph and a world map graph. We divide the graph into 300 pieces or 1,000 pieces. So these are graphs actually that we can handle with a good machine in memory and solve like with a good algorithm. But we wanted to see what happens if we distribute the computation. So what we observed was that when we divide the graph into 300 pieces, we lost like 50% of the optimum. And like when we divided to 1,000 pieces, we lost 58% of the optimum. So this is like one place that we observe, okay, like now if we have a graph with trillions of edges, we can still apply this problem, this framework, and lose, yeah, like some percentage of the optimum, but still like be reasonably fine. The more challenging class of problems that we solve in this framework is what we call maximum submodular maximization or maximum coverage. So for example, you're given a family of subsets, and you want to choose k subsets that maximize the cardinality of the union. So max coverage is where you want to choose k subsets S1, S prime 1 to S prime k, and maximize the cardinality of the union. A generalization of this problem is what we call submodular maximization, where you're given a submodular function defined on any subset of elements. So here, like for the coverage problem, the elements are the sets themselves. And you want to find a set of size k that maximizes f of s. So more about why we care about submodular maximization, you can formalize different variants of data summarization, feature selection, facility location problems. And submodular functions are defined like this. So submodular function, a set function is submodular if it satisfies this diminishing return property. For any two subsets A and B, f of A plus f of B is at least f of A union B plus f of A intersect B. So the bad news for submodular functions is that if I divide the data set arbitrarily among m machines and try to apply this idea, it does not work. You don't get a factor better than square root of k. So no matter how you divide the data, no matter what algorithm you apply in the second stage, basically if the partitioning is at random, you don't hope to get a good core set from each basically machine. So, but on the other hand, we observe that randomization helps a lot here. So instead of dividing the data arbitrarily at random, you divide it, instead of dividing it arbitrarily, you divide it at random. For example, even like with uniform, like in each element, you just send it to one or epsilon, like some number of machines. So like when you do this random partitioning and you run greedy algorithm on the first stage and greedy algorithm on the second stage, you get basically a much better result. And the theorem is that if you do very simple algorithm like this, you get a 1/3 approximation. And if you do fancier algorithms, you get like better approximation factors. And the performance and the effectiveness of these algorithms have been confirmed in like a couple of NIPS and ICML papers already. So I think the summary of the composable core set part, the theoretical part of the talk, was that for a different set of problems, like diversity maximization, clustering, the submodular maximization, and coverage problems, you can apply this idea and get a good distributed algorithm. So the third part of the talk, which is less theoretical, but more related to the parts that we combine an algorithm and the right systems. So first of all, in order to develop this library, we have tried various like different type of frameworks. Like we use like vanilla MapReduce at some point. The one that we use the most is what we call iterative MapReduce or Flume with a like big table service or a distributed hash table service. It's like a read-only distributed memory service that we can have random access to the data. But when we use distributed hash table service, we load only the nodes of the graph into memory, in distributed memory. We do not load edges of the graph, and that's very important. We also applied, like at the beginning, we applied Pregel type technique, like framework, but then we moved away from that because we realized in terms of fault tolerance, it's not as good as these other frameworks. And more recently, we have applied some asynchronous message passing framework. So like when we want to measure the quality of a MapReduce algorithm, we care about the running time, we care about the communication complexity between machines. So we have to make sure that we do the like minimum amount of communication. We care about load balancing among reducers. So I'm also assuming that you know what MapReduce is and so on for sure. And like the locality of messages. So I just want to give you the story behind the simplest two-state clustering problem, the connected component problem, where you want to find all connected pieces of a huge graph. So we are dealing with, for example, a graph with 700 billion edges here, and finding connected component in this graph is not as easy as one can say. The reason is that we will have a very huge connected component. In this case, like a connected component with 5.8 billion edges among like 8 billion edges. And finding this connected component is very hard. So what we have done is to develop like algorithms in all these framework based on connected component and see which algorithm works best in practice. And also like prove properties of those algorithms. So like in a paper in 2014, we report basically a simple algorithm, a class of simple algorithms that provably converge to the optimum to connected component in log square rounds. Like we have a variant of the algorithm that is only MapReduce. We have a variant of algorithm that uses distributed hash table service and improves the number of rounds to log n. But the most important thing is that we apply this to several public and public available data sets. So in general, for the MapReduce algorithm that has some guaranteed convergence, we get 10 to 20 times faster running time compared to the best externally known algorithm that we knew of, and like it's the hash to mean algorithm. I don't have time to elaborate on that. Then the MapReduce plus the distributed hash table service framework actually gives us an edge, like sometimes 10 times faster than the best MapReduce algorithm. And the new asynchronous message passing framework gives us even better running time with much less resource consumption. So maybe in the next couple of minutes, I'll also tell you about this async framework that we are finally writing and putting on archive. So this is a simple graph mining framework that basically runs asynchronous computation or like message passing among nodes. So it's both very far torrent and it's like has impressive empirical performance. So in this framework, nodes are distributed among machines. Each node keeps state and send messages to its network to its neighbors to update their states. So each machine has a priority queue to decide which messages to send to other machines. So there are like 3 steps to write a program in this framework. There is an initialization stage where you want to initialize each node like the state, and then there's a propagation loop that says upon receiving basically messages from your neighbors, how do you update your state? And these message passing happens completely asynchronously. So a very simple implementation of connected component on top of that graph, on top of that framework. We applied it on different type of data sets. The largest data sets that we have had here are has in the order of 10 trillion edges. And we comfortably solve connected component problems on top of those. And basically report that our simple implementation on async outperformed the best MapReduce implementation that we have had. So the message here was that for some simple graph computation problems like connected component and shortest path, and if you don't want to solve balanced partitioning, you don't need too much synchronization. This framework gives you a very nice and fast solution. But then you can say there are other asynchronous frameworks around. The beauty of this async framework is that it also provides a very nice fault tolerance that upon failure or preemption of many machines, it can survive and give you a reliable solution. So we have also in the paper that we are going to put on archive report some results of when we make machines fail, for example, in the process of running the algorithm, how fault tolerant we are. For example, if we make the total of 50% of machines across the running time of the algorithm fail, artificially we increase the running time by we double the running time and not worse. So basically, and then we also report what different patterns of failures can increase the running time. And this is I can't emphasize more how important is this fault tolerance when you want to develop a graph mining library for others, a graph mining library that you can't babysit for large data sets. So to summarize, the 3 algorithmic techniques that we apply in this library are local message passing algorithms. The first one, so for example, we compute personalized PageRank vectors, and we solve connected components with these type of techniques. We apply embedding and sketching and locally sensitive hashing techniques. So I talked about this embedding idea to a line, but we use locally sensitive hashing to build the graph and to mine the graph a lot. So this is something that I didn't emphasize here, but it's one of the most useful and applicable techniques that we use in practice. And then the idea of randomized composable coresets that I summarized. And moving forward, we are trying to improve our tools, in particular by developing tools that makes the assumption that you can load the graph into memory, or at least the whole graph into distributed memory. So the problem becomes much easier if you can basically have the graph into all the edges of the graph at least in memory. And yeah, you can get some improvements, but these solutions are not as scalable as the ones that we have developed. And like we are trying to take advantage of this EgoNet mining framework, and Alessandro will give a talk about that. We are also integrating with other machine learning tools at Google and elsewhere. Like basically, we want to combine the learning stage of our algorithms and like graph mining or graph building stage of algorithm, and for example, develop what we call graph learning techniques. And last not least, Brian Perosi in our team is like trying to develop basically deep walk-based methods to improve compute new embedding in the or apply neural networks to do better network inference. We are also working on developing better algorithms to come up with experimental units for different type of experiments under network interference. So I think I wanted to give you a sense of what we have been doing like in the past many years. Like I mentioned many results and like some pointers to papers, and I'm hoping that you can go read them. I can emphasize how important this basically graph mining library have been for our other applications, for market algorithm applications where we want to identify sub-markets of advertisers, sub-markets of queries. It empowers us and like the rest of Google for these type of applications. And I invite you to look at some of these pointers as well. Thank you.